Welcome to the week 7 of SRM course on Introduction to Electric Vehicles and Hybrid Electric Vehicles. Myself, Dr. Venu Sonti, Assistant Professor in Department of Electrical Engineering, National Institute of Technology, Raipur. In the last topic, we have discussed about the construction and working of brushless DC motor along with its speed control techniques. This week, our focus will shift to switched reluctance motors used in electric vehicles. We will delve into their construction, working principles and modes of operation. By the end of this week, you will have a comprehensive understanding on how SRMs are utilized to optimize the performance and efficiency in EVs. A switched reluctance motor is a type of electric motor that operates by the principle of variable reluctance. It converts electrical energy into mechanical energy by the attraction of its rotor to minimum reluctance path created by the magnetic field in its stator windings. The rotating magnetic field is created with the help of power electronic switching circuit. An SRM, also referred as variable reluctance motor, operates based on principle of variable reluctance. This principle means that the rotor always seeks to align itself along the path of lowest magnetic reluctance, minimizing resistance within the magnetic circuit. As the stator windings are energized in sequence, the rotor adjusts its position to align with stator's magnetic field, creating rotational motion. The switched reluctance motors are gaining popularity in adjustable speed drives due to their advantages like this motor is simple in construction with no winding on rotor and simple concentrated coils on stator. It can run successfully at high speeds because of no winding on rotor and rugged rotor construction. Stator windings can be easily and efficiently cooled in switched reluctance motors. The switched reluctance motors can operate successfully through with reduced output even if one or more phases are out of the circuit due to a fault. As these motors can be manufactured with large number of stator and rotor teeth, they give larger torque per unit volume. Next, coming to the construction of switched reluctance motor. The switched reluctance motors have two distinct constructions. The first one is the singly salient construction, second one is doubly salient construction. In both the types of switched reluctance motors, the stator and rotor magnetic circuits are laminated to reduce the core losses. Now coming to the singly salient construction. In a singly salient construction of switched reluctance motor, we have non-salient stator and a salient rotor. In this design, the rotor does not have any windings while stator is equipped with the winding. So, in this figure you can observe the singly salient construction of switched reluctance motor. Here on the winding on the rotor there are no windings, but we have here a cylindrical stator consists of two phase winding. Next, coming to the doubly salient construction. In doubly salient construction of switched reluctance motor, both the stator and rotor features salient poles. This means both components have distinct projections or poles that enhance magnetic interaction. From this figure, you can observe the construction of doubly salient switched reluctance motor. Here we have 4 salient poles on the stator and 2 salient poles on the rotor. For the same frame size, a doubly salient switched reluctance motor generates more torque compared to the singly salient motor. Next, coming to the working of switched reluctance motor. To explain this working of switched reluctance motor, let us consider a 3-phase 6x4 switched reluctance motor. On the stator we have 6 poles and on the rotor we have here the 4 poles. As shown in the figure A, the phase winding A is excited and the rotor is oriented as shown, and the flux linkages are maximized with phase winding A. When phase winding A is de-energized and phase winding B is energized, The rotor moves in counterclockwise direction so as to maximize the flux linkages with winding B as shown in figure B. Next, to achieve the further counterclockwise rotation, phase winding B is de-energized and phase winding C is energized. Now, the rotor rotates in counterclockwise direction following the clockwise excitations, that is ABC. The phase currents in the stator phases are switched on and off in synchronization with the rotor positions, ensuring continuous rotor rotation and development of steady average torque. Proper synchronization of switching of phase windings with rotor position is crucial for maintaining this continuous rotation. To achieve this, a Hall effect type shaft mounted sensor is essential as it determines the rotor position and controls the turning on and off of appropriate phase windings. Next, if you see the block diagram of 3-phase switched reluctance motor drive system. So, in this block diagram we have a diode bridge rectifier, an LC filter, a power converter, a 3-phase 6x4 switched reluctance motor and a controller. As can be seen here, the AC supply is first converted into the DC via rectifier, and then the power converter controls the switched reluctance motor through its switching action. The controller, which is the brain of entire system, sends the control signals to manage the timing, sequence and duration of current pulses to the motor based on the feedback from motor and the desired operating conditions. A rotor position sensor is used to detect the position of rotor relative to stator, which is crucial for determining when to switch the stator windings on or off. Next, coming to the torque production. Assuming magnetic linearity, the reluctance torque generated in the switched reluctance motor is given as Te equal to half I square dl by d theta. Here I is the instantaneous value of the exciting currents in the phase winding and L is the self inductance of phase winding. As the torque is proportional to square of current, it remains independent of current direction. However, the sign of torque depends on how the inductance varies with the rotor position theta. To explain this, let us consider figure A with angle theta set to 0. Here the inductance is at minimum position L minimum. Here side A of rotor pole 1 aligns with the left tip of stator pole. As the rotor moves in clockwise direction, the overlap between stator and rotor poles increases, leading to a decrease in reluctance and a linear increase in inductance. When theta equal to theta 1 as shown in figure B, the pole faces are fully aligned, resulting in minimum reluctance and maximum inductance L max. For rotor movement from theta 1 to theta 2, the reluctance remains minimal, so the inductance stays constant at maximum value over the overlap angle theta 2 minus theta 1. Once the rotor moves beyond theta 2 as shown in figure C, the overlap between stator and rotor pole faces begin to decrease. Consequently, reluctance increases and inductance start to decrease. When theta equal to theta 3 as shown in figure D, the inductance decreases to its minimum value L minimum, which is same as that the inductance at theta equal to 0 shown in figure A. For rotor movement from theta 3 to theta 4 equal to 180 degrees, the inductance remains at constant L minimum. Beyond theta 4, the inductance begins to increase linearly, similar to the earlier case. Now, if you observe the induction variation of stator phase winding with respect to theta, here from 0 to theta 1 degrees, the inductance increases from L minimum to L maximum. From theta 1 to theta 2, the value of inductance is constant at L maximum, and from theta 2 to theta 3, the value of inductance decreases from L maximum to L minimum. From theta 3 to theta 4 equal to 180, again the value of inductance is constant at L minimum. Next, coming to the torque angle characteristics. Here from 0 to theta 1, we have a average positive torque, and from theta 1 to theta 2, here we have the 0 torque, and from theta 2 to theta 3 we have a average negative torque, and from theta 2 to theta 4 again you have the 0 torque. From the torque angle characteristics, it can be observed that reluctance torque is positive when dl by d theta is positive, and the reluctance torque is negative when dl by d theta is negative. No reluctance torque is generated when inductance remains constant. Analyzing the torque angle characteristics reveals that average torque is 0 when the winding current is constant. However, a positive average torque is produced when a phase winding is energized during this period when dl by d theta is positive and not when dl by d theta is negative. This method is applied to all the stator windings sequentially, ensuring that a positive torque is developed, allowing the rotor to rotate. Next, coming to the operating modes of switched reluctance motor. The switched reluctance motor functions in two distinct modes, single pulse mode and pulse width modulation mode. These modes are defined by the nature of current waveforms within the phase windings of switched reluctance motor. Coming to the single pulse mode. In single pulse operation, the increase in current is carefully controlled within specific limits during each brief period of phase excitation. This controlled rise in current is influenced by two key factors: the inductance of winding and counter electromotive force generated by the movement of rotor within the stator winding. The winding inductance, which is the property of winding that resists change in current, plays a crucial role in shaping the current rise. Additionally, the counter EMF, which is produced as the rotor moves, opposes the applied voltage and affects the overall current behavior. An illustration of ideal current waveform along with the variation of inductance as a function of rotor angle theta is presented in figure A. This figure provides a detailed view of how the current evolves and how the inductance changes in response to the rotor's position. In the diagram provided, the behavior of circuit can be described as follows. As the inductance L theta starts to increase, the switch is closed, which allows the current to flow through the circuit and quickly stabilize at a constant value. This is due to a fact that inductor's resistance to change in current results in steady state current once the switch is turned on. When inductance ceases to increase and reaches a stable level, then the switch is opened. This action causes the current to drop to 0 almost instantaneously, as there is no longer a continuous path for current to flow. Throughout the period when current is constant and positive, the increasing inductance L theta generates a positive torque in the system. This is because the rising in the inductance creates a varying magnetic field that produces a torque effect. However, it is important to note that such idealized waveforms where the current changes instantaneously and inductance varies in a perfectly controlled manner are not practically achievable. In practical applications, it is crucial to adjust the timing of switching the phase windings relative to the rotor angle theta to optimize the torque generated by the switched reluctance motor as shown in figure B. From this figure, it is clear that the source voltage Vs should be applied to the winding slightly before the inductance L theta starts to increase. By doing so, the current I theta can build up more rapidly to high value before the region where torque generated begins. This primitive application of voltage takes advantage of low inductance phase to facilitate a quicker rise in current. Once the rotor reaches theta 1, the current I theta starts to decrease due to combined effect of increasing inductance L theta and rotational EMF. The switch remains closed until the rotor angle reaches theta 2. At this specific angle theta 2, a negative voltage is then applied to the phase winding to to control the current flow and manage the torque production effectively. This causes rapid fall of current and finally I theta reduces to 0 at extinction angle theta 3. Angle theta 2 minus theta naught is the conduction angle of the switch and theta 3 minus theta 2 is the diode conduction angle of the inverter. The theta naught is normally called as switch on angle and theta 2 is called the switch off angle. The theta 1 minus theta naught is called angle of advance. Applying the negative voltage to the phase winding well before maximizing inductance L theta is reached is essential to ensure that current decays to 0 and prevent entering to a negative torque region. This advance in timing helps in managing the current effectively and maintaining optimal motor performance. At higher motor speeds, it becomes necessary to increase the angle of advance significantly. This adjustment allows the phase current to rise quickly to a substantial value before inductance begins to increase, which is crucial for efficient operation at these speeds. For regeneration purposes, it is important that current pulses and the decrease in inductance occur simultaneously. During the regenerative braking mode, the current through diode surpasses the current through thyristor, leading to the return of net energy to DC source. Overall, the switch angle, angle of advance and switch off angle are critical parameters that control the operation of switched reluctance motor drive. Next, coming to the PWM mode of operation. In this operating mode, often referred to as low speed mode, each phase winding of switched reluctance motor is energized for an extended duration. During this prolonged excitation, the current can potentially build up to very high values which may exceed safe operational limits for both motor and inverter components. To manage and control the current effectively, a current limiting device is employed in conjunction with the SRM. This is accomplished by installing a current sensor in each phase winding. The role of current sensor is to continuously monitor the current levels and ensure they remain within acceptable bounds. The current sensor communicates with control system which adjusts the speed of the operation of power converter components accordingly. By alternatively switching the converter components on and off, the system regulates the current flow, keeping it within predefined upper and lower limits. This approach prevents the current from rising to excessively high levels, thus producing both the motor and inverter components from potential damage and ensuring reliable operation of the switched reluctance motor. Figure C illustrates the phase current of switched reluctance motor as it varies with rotor position theta. In this graph, I max and I minimum represents the upper and lower limits of chopped phase current, while I naught denotes its average or mean value. Additionally, the graph displays how the inductance changes with rotor position. When the upper and lower limits of phase currents are adjusted, either increased or decreased, the mean value of motor currents will also change. This adjustment in mean current directly influences the torque produced by the motor. Consequently, modifying these current limits enables precise control over torque and allows for adjustment of motor speed to meet specific operational requirements. Next, coming to the speed torque characteristics of switched reluctance motor. The torque speed characteristics of switched reluctance motor drive can be divided into three regions. The constant torque region lies below the base speed omega b, which represents the highest speed at which motor can receive maximum rated current at rated voltage with fixed firing angles. Essentially, omega b is the minimum speed required for motor to operate at its rated power. First, coming to the region 1. In the low speed region, the back EMF is minimal, allowing the current to rise almost instantly after turn on. The current can be regulated to any desired level using controllers such as hysteresis controller or voltage PWM controller. As motor speed increases, the back EMF begins to match the DC bus voltage, requiring an advance in turn on angle to ensure that current reaches to desired level despite the lower back EMF. Maximum current can still be supplied to the motor using PWM or chopping control to maintain maximum torque. Additionally, the phase excitation pulses must be placed turned off before the rotor aligns, allowing freewheeling current to decay and preventing the generation of braking torque. Next, coming to the region 2. At high speeds, when the back EMF exceeds the DC bus voltage, the current starts to decrease as pole overlap begins, making PWM or chopper control ineffective. With fixed supply voltage and conduction angle theta dwell, also known as dwell angle, the phase excitation time and current decrease inversely with speed. Since torque is proportional to square of the current, the torque speed characteristics follows the relation torque inversely proportional to speed. Increase in the conduction angle can sustain torque by delivering more effective amps to the phase. In this constant power region, torque is maintained inversely proportional to speed by adjusting theta dwell until it reaches its upper limit at omega p, allowing for a wide range of high speed operation. Next, coming to the region 3. When theta dwell reaches its upper limit, it can't be increased further because flux would not return to 0 and current conduction would become continuous. In this region, torque governed by a natural characteristics falling off 1 by omega square, similar to a DC series motor. The torque speed characteristic of switched reluctance motor are similar to those of DC series motor, which is not surprising considering that back EMF is proportional to current and torque is proportional to square of the current. Next, coming to the inverter drive circuits of switched reluctance motor. These are the inverter drive circuits for switched reluctance motor. As mentioned earlier, the phase windings of switched reluctance motor require a unidirectional current pulse when rotor is in correct position. The inverter must apply a direct voltage to the phase windings when rotor is in correct position. When it is necessary to turn off the phase winding, the inverter configuration should offer an alternative path per rapid reduction of phase current. These requirements are met by the inverter drive circuit shown here. Figure A and B illustrates the inverter drive circuits for single phase winding, while figure C shows the configuration for two phase winding. These circuit designs can be expanded to accommodate the excitation of additional phase windings. As illustrated in figure A, when switch S is closed, the primary winding is energized with current flowing in direction as shown and energy is supplied from source to the phase winding. When switch S is opened, the decaying current in primary winding induces a voltage in secondary winding which forward bias the diode D. The current from primary winding is then transferred to the secondary winding through transformer action, gradually reducing to 0. The stored energy in the motor's magnetic circuit is returned back to the source. This process, known as regeneration, results in more efficient inverter configuration as the magnetic stored energy is not dissipated as heat, but rather fed back to source. The inverter circuit depicted in figure B utilizes two switching devices and two feedback diodes for each phase. Both switching devices S1 and S2 operate simultaneously, allowing current to flow through the phase winding as shown by arrow, enabling the energy transfer from source to phase winding. Once S1 and S2 are turned off, the current continues to flow in same direction but starts to decay. This decay generates a voltage across phase winding which forward bias the diodes D1 and D2, allowing most of the stored inductor energy to be returned back to DC source. The inverter configuration shown in figure C features two DC sources each with voltage Vs requiring one switch and one diode per phase. Phase 2 is connected oppositely to phase 1. When switch S1 is closed, the phase winding 1 receives excitation from upper DC source. Upon opening switch S1, the decaying phase current forward bias diode D1, allowing the current through flow through lower DC source, diode D1 and phase winding 1, transferring inductive energy to lower DC source. Thus, phase winding 1 is powered by upper DC source while regenerating into the lower DC source. Similarly, phase 2 is powered by lower DC source and regenerates into upper DC source. Next, coming to the advantages of switched reluctance motor. The first advantage is the natural cooling. As the switched reluctance motor do not require an external ventilation system due to the projected slots in stator and rotor, allowing for natural airflow between the slots which helps in cooling. The second advantage of switched reluctance motor is no rotor windings. The rotor is devoid of windings, eliminating the need for carbon brushes and slip ring assemblies, which enhances reliability and reduces the maintenance. The third advantage of switched reluctance motor is cost effectiveness. The absence of permanent magnet reduces the cost of the motor, making switched reluctance motors more affordable compared to the other motor types. The fourth advantage is the simple control requirement, as simple 3 or 2 phase pulse generator is sufficient to drive the motor, simplifying the control systems. The fifth advantage of switched reluctance motor is self-starting. The switched reluctance motors are self-starting and do not require additional external arrangements, making them convenient for various applications. Next, coming to the disadvantages of switched reluctance motor. The switched reluctance motor have high torque ripple. Due to this high torque ripple, there will be higher vibration and high acoustic noise. The design of switched reluctance motor must account for magnetic saturation, which can limit the maximum torque and speed capabilities. The switching action in switched reluctance motor can produce higher levels of electromagnetic interference, which may require additional measures to mitigate in sensitive applications. In case of switched reluctance motor, external rotor position sensor is required, which increases the cost of the system. Now, to summarize the week 7 of SWAYAM course on introduction to electric vehicles and hybrid electric vehicles. First, we have started our discussion with the induction motor. We have discussed the basics of induction machine like construction, working, speed torque characteristics, next speed control of induction machine and the vector control of induction machine. After that, we started our discussion with permanent magnet synchronous motors. We have discussed about the basics of permanent magnet synchronous motors like construction, working and speed control techniques. Next, we moved our discussion to the brushless DC motors. In the brushless DC motors, we started with the construction followed by working. Also, we have discussed about the speed control techniques of brushless DC motors. Next, we moved our focus to the switched reluctance motor. In this switched reluctance motors, we have discussed about the construction of switched reluctance motors, next modes of operation of switched reluctance motor, speed torque characteristics of switched reluctance motors, next the advantages of switched reluctance motors and disadvantages of switched reluctance motor. With this, I am going to conclude our week 7 of SWAYAM course on introduction to electric vehicles and hybrid electric vehicles. Thank you.